It is not practical to draw a Lewis structure for all compounds, but especially larger ones that you would find in organic chemistry. Bond line structures simplify the drawing process and are also easier to read for people who are trained properly. Here we can see an example of a bond line structure of amoxicillin. As you can see, most of the atoms are not drawn. Bond line structures are drawn in a zigzag format, and at each endpoint or corner represents a carbon atom. Here you can see 3 examples of compounds that all contain 6 carbon atoms. Double bonds are shown with 2 lines, and triple bonds are shown with 3 lines, as you can see in the 2 examples at the bottom right. As you can see, triple bonds are drawn in a linear format rather than a zigzag format. This is because triple bonds involve sp hybridized carbon atoms, which will have linear geometry. All other bonds are drawn in zigzag formation. Here you can see an example of a compound with 8 carbon atoms. Hydrogen atoms bonded to carbon are not shown in bond line structures, as they are assumed that each carbon will possess a hydrogen unless otherwise stated. Familiarity with bond line structures will allow you to see all hydrogen without them being drawn. Here we have a practice problem asking us to identify the number of carbon atoms in diazepam and fill in all missing hydrogen atoms. Each carbon atom should have 4 bonds. We therefore draw enough hydrogen atoms in order to give each carbon atom a total of 4 bonds. Any carbon atoms that already have 4 bonds will not have any hydrogen atoms. Here you can pause to view the final answer. When drawing bond line structures, the following rules should be observed. First, carbon atoms in a straight chain should be drawn in a zigzag formation, as you can see in the picture below. The second rule is, when drawing double bonds, draw all bonds as far as possible, as you can see in the example below. The third rule is, when drawing single bonds, the direction in which the bonds are drawn are irrelevant, as shown in the 2 examples provided below. The fourth rule is all heteroatoms, which are atoms other than carbon and hydrogen, must be drawn, and any hydrogen atoms attached to a heteroatom must also be drawn. As you can see in this example, the oxygen heteroatom has to have the H drawn with it. The fifth and final rule is to never draw a carbon atom with more than 4 bonds. Carbon only has 4 orbitals in its valence shell, and therefore carbon atoms can form a maximum of 4 bonds. Here we have a practice problem asking us to draw a bond line structure for the following compound. First, we're going to delete all hydrogen atoms except those connected to heteroatoms. Then, place a carbon skeleton in a zigzag arrangement, making sure that any triple bonds are drawn as linear. And then finally, delete all carbon atoms and you get your final answer. A formal charge is associated with an atom that does not exhibit the appropriate number of valence electrons. When a carbon atom bears a positive or negative charge, it will only have 3 rather than 4 bonds. Lone pairs are often not drawn in bond line structures. It is important to recognize that lone pairs are present when you do draw bond line structures. Here we have a practice problem asking us to draw all of the lone pairs in the following structure. The oxygen atom has a positive formal charge and 3 bonds. It is preferable to recognize the pattern that a positive charge and 3 bonds means that the oxygen atom has just 1 lone pair. Here we have another practice problem asking us to draw any lone pairs associated with the nitrogen atom. The top nitrogen atom has a positive formal charge and 4 bonds. The bottom nitrogen has 3 bonds and no formal charge. It is preferable to simply recognize that the top nitrogen must have no lone pairs, and the bottom nitrogen must have one lone pair. In bond-line structures, a wedge represents a group coming out of the page, and a dash represents a group behind the page. In certain circumstances, there are other types of drawings that can be used, all of which indicate three-dimensional geometry. Here are three examples of three-dimensional bond-line structures. Bond-line structures are inadequate in some situations, and the approach that chemists use to deal with the inadequacy of bond-line structures is called resonance. Resonance structures are separated by double-headed arrows and surrounding brackets as shown in the example below. Resonance stabilization refers to the delocalization of electrons via resonance. Curved arrows are tools for drawing resonance structures. When drawing curved arrows for resonance structures, remember these two rules. First, avoid breaking a single bond when drawing resonance structures. By definition, resonance structures must have all the same atoms connecting in the same order. Breaking a single bond would change this, hence this is the first rule. The second rule is never exceed an octet for second row elements. Elements in the second row only have 4 orbitals in their valence shell. Each orbital can either form a bond or hold a lone pair. Therefore, for second row elements, the total of the numbers of bonds plus the number of lone pairs can never be more than 4. They can never have 5 or 6 bonds. 4 is the most. Here you can see some examples of curved arrows that violate this second rule. In each of these drawings, the central atom cannot form another bond because it does not have a 5th orbital that can be used. Here in our last practice problem, it asks us to rank the following resonance forms, from most to least significant. We begin by looking at any atoms that lack an octet in any of the resonance forms. Structures A and C both have them filled. However, in structure B, the carbon atom with a positive charge only has 3 bonds, for a total of 6 electrons, so it lacks the octet. Therefore, structure B is the least significant. Next, we look for formal charges, and since structure C has filled octets and no formal charge, it would be ranked the most significant, leaving A as the second best.